Hi, my name is Meera and this is my exam wrapper for exam one. The problem I'm going to be going over is problem number two. Problem number two, I missed a good amount of points on, so I wanted that to be the one that I did my exam wrapper on. For part A, there are 6 diagrams, and you are supposed to label 4 of the diagrams with the corresponding charge figure that matches it. So the reason I got at least part of this wrong is that in number one, it says the charged ball is initially far away from the objects as labeled here. And in not reading that, I put K, which signifies something neutral, when it should have been B. So that makes sense. Then the ball is brought close to an uncharged copper block without touching it. Then the ball swings toward the block. In this instance, the correct answer should have been G and not D. G because the ball is already negatively charged, and those negative charges start moving toward the uncharged block, as shown in G right here. Then parts four, part four just means the ball briefly touches the block. Part five, when the ball is moving away, and part six, when it is attracted to something else negative. Both are correct in the answer being H, which shows a larger distribution of negative charges on the left side of the object, which is away from the neutral block, which is away from the negatively charged pen. And this makes sense because the block, which was once neutral, is now also negatively charged. Same with the pen, so the letter for these two should be the same, which makes sense. Part two of this problem deals with 3 blocks that are movable, and the problem asks us to find how block C, which is originally neutral, can end up with a negative charge. So block A starts off with a positive charge, and block B is neutral. But if A polarizes B, B ends up with a charge distribution of the left side having negative charges and the right side having positive charges, but a net overall charge of 0. Then the same concept can be done with block C due to the positively charged block A. So you polarize C in the same fashion, again with negative charges on the left side and positive charges on the right. Now, if you combined C and B together with C on the left and B on the right, that's very important, the charges in the middle here become neutralized, as you can see. So the left side of C and the right side of B end up being neutral together. However, if you separate block C and B, block C ends up with just those negative charges shown above, and block B ends up with the positive charges on the right. And then after a while, the negative charges on the block C spread out and distribute over the surface, leaving C with an overall negative charge on its surface. So part 3 of number 2 asks the student to explain briefly why the attraction between a point charge and a dipole has a different distance dependence for induced dipoles as for permanent dipoles. So the distance dependence for induced dipoles, if you can't see that, is 1 over distance to the fifth, which is a lot less than for permanent dipoles, which is 1 over the distance, or r cubed. So in understanding this, there's 2 ways you can go about it. One, using the formula for an induced dipole and how the separation distance that you calculate for that ends up making the distance dependence a lot more than what it was for a permanent dipole. But if you think about it conceptually, an induced dipole is one that is not a dipole on its own. It's due to an external applied electric field. And because of that, the distance dependence is more important and therefore more severe as distance increases, because whatever is externally applying that force will cause the induced dipole to become weaker and weaker as that molecule is further and further away from that induced dipole. And after a certain point, that induced dipole will go back to its unpolarized state because the dipole, again, is not permanent. It's induced by an external electric field.